Hello, I'm Srihari Sangaraju. I recently finished my PhD here in structure, seismic and geotechnical engineering. My PhD is funded by Marie Curie Fellowship under the supervision of Professor Roberto Paolucci, and my research is about performing 3D physics-based earthquake ground motion simulations, considering the wave propagation from the earthquake source down under and the soil until the structures. We know that earthquakes can be devastating. The way ground shakes depends from neighborhood to another neighborhood. Engineers tackle the risk from these earthquakes by depending on the seismic hazard maps. However, the classic seismic hazard maps are uniform over large regions. This work will be the foundation to improve these seismic hazard maps by performing earthquake simulations to gather the site-specific ground motions. 3D physics-based simulations are gaining attention for simulating these site-specific ground motions. These simulations model the region by considering realistic geology and realistic earthquake source. However, they have some limitations. For example, the accuracy of these simulations depends on the assumptions that we make, and these are computationally expensive, especially when we have to consider the small features like the soil sediments and the buildings. So in this PhD, I try to address these issues by implementing numerically efficient computational tools in the speed code to perform fully coupled simulations without increasing the computational demand. Speed code is developed in Polyme itself and is used for earthquake simulations. In the first stage, we have performed a validation exercise to check if the 3D simulations can simulate the site-specific ground motions. So for this, we have simulated the ground shaking during the 2016 Kumamoto earthquake sequence. The simulated ground motions have captured the observed low-frequency features like the pulse-like ground motions, and also because of the top few meters of the soil, we can see that the seismic energy is trapped inside the basin. To further study this site response, we need to perform fully coupled 3D nonlinear simulations. However, they are very rare in the literature because of the computational expenses. So we first implemented an efficient nonlinear constitutive model in speed code, and then we used the same module to perform large-scale 3D nonlinear simulations. Further, we have also implemented another module in speed code to couple the building response with the 3D simulations. In general, when we have to model buildings inside the mesh, the simulations will be computationally expensive. So what we do is we assume the buildings as simple MDOF systems, and then at each time iteration in the simulation, we exchange the forces from the soil and the building. This will be useful to understand the site-city interaction effects and also to perform the damage scenarios at an urban scale. In conclusion, we have developed all the ingredients that are needed to perform fully coupled simulations, and we can use this in near future to understand the physics or to generate the site-specific ground motions. Thank you.